Hello everyone, welcome to the lecture 39 of the course Diffusion in Solids. So we have been talking about the different techniques to measure the diffusion coefficients. Continuing that, today we are going to start with the methods that utilize the nuclear spin. And this will be covered in two lectures today and one more which follows this one. So today we will talk about the nuclear magnetic relaxations, spin and spin lattice relaxation, and how these techniques or these phenomena help us calculate the diffusion coefficients, or rather how they are affected by the diffusion of atoms. So this nuclear magnetic relaxations, NMR or nuclear magnetic resonance, these can provide information on diffusion through the influence of atomic movement on the width of nuclear resonance lines and on the relaxation times. So this is what is the basis of all the NMR different methods that we are going to talk about, that the different types of the nuclear resonance lines or the relaxation times, what happens when there is no diffusion of atoms and what happens when there is a diffusion of atom. So this influence of atomic movements on the width of these lines or on the relaxation times is what helps us deduce the diffusion coefficients. So because the atomic diffusion implies that there is a fluctuations of the local fields. Also the fluctuating fields implies that magnetic dipole interactions of the magnetic moments or nuclear electric quadrupole moments with internal electrical field gradients. Now the external magnetic field gradients can also be used to determine the diffusion coefficients. And if you remember the very first lecture when we started talking about the diffusion measurement techniques, we have seen this particular picture which tells about the direct measurement techniques and the indirect measurement techniques and the range of diffusivities that can be measured using them. And you will see that the NMR related techniques feature in both. So you have the field gradient NMR, which comes in the direct measurement techniques. Then you have NMR based methods like QENS and MBS, which falls under the indirect measurement techniques. So that way it is very useful to basically determine the diffusion coefficients. So this technique or these type of methods are very useful. Now let us first start with a little bit of fundamentals of NMR. So NMR basically, as the name suggests, it is applicable to atoms with non-vanishing nuclear spin moment, which is given by h bar into I. And this mu is which is rather proportional to h bar into I, and mu, the nuclear spin moment is equal to gamma into h bar into I, where gamma is known as the gyromagnetic ratio, and this h bar, I think you know, is h by 2 pi, where h is the Planck's constant. Now when you are in a static magnetic field, let's say B naught in z direction, a nuclear movement mu performs a precession motion around the z axis governed by the equation du mu by dt is equal to mu cross B naught. What is meant by precession? Precession is a movement like this, where this is your nucleus, and this is the mu, which is the nuclear dipole moment. So the precession happens like this. So it is a movement like this. I'm sorry if I am not being accurate, but this is how the precession motion is. So this is your applied magnetic field B naught, and this is the rotation of the nucleus, and this is how the nuclear moment performs a precession motion around the z axis. So this is governed by the equation d mu by dt is equal to mu cross B naught. And the frequency of this motion, the frequency of the precession, which is also known as the Larmor frequency, it is given by omega naught equal to gamma into B naught. Remember, gamma is the gyromagnetic ratio. The energies of nuclear magnetic dipoles are quantized, and they are quantized according to the expression is equal to minus m gamma h bar into B naught, where m can vary from minus I to plus I. So, it can take the value minus I plus 1, I minus 1, I, and so on. So, when you have an ensemble of nuclei, the equilibrium magnetization is actually given by this expression n into gamma square h bar square I plus 1 divided by 3 kBt into B naught, where B naught is the static magnetic field in the z direction, and the magnetization, as the name suggests, is the magnetization of the nuclei. So, each nuclei gets magnetized when it is placed in a static magnetic field, and if we talk about the ensemble of nuclei, then the equilibrium magnetization is given by this expression, where n refers to the number density. Now, in a typical NMR setup, what you do is you have a B naught, which is a static magnetic field which is homogeneous and strong of the order of few Tesla. Then you have an alternating magnetic field perpendicular to the z direction. So, you have this is B naught and this is the direction of your B1, which is an alternating magnetic field usually produced with the help of electromagnets. And usually this comes the frequency of this magnetic field omega, this falls under the radio frequency. So, they are also called as the radio frequency fields. Now, if omega is equivalent or it is approximately equal to the Larmor frequency, this will induce the transitions between the Zeeman levels of the nuclear spins. Now, this movement or this magnetization is actually governed by what is known as the Bloch equation. So, which says that, so you can see here it is dm by dt, that means the rate of magnetization. What it is talking about is the rate of magnetization, which has this 4 different terms, gamma m cross b minus m perpendicular by T2 minus mz minus mz equilibrium by T1 plus gradient of d times gradient of m minus m equilibrium. So, remember there are 4 terms here. What are these 4 terms? Let us try to look at that. So, the very first term is the precession of the spins around the magnetic field B. Okay. So, this m cross b, like we saw in the previous case, you saw here that d mu bar by dt is equal to mu cross b naught. Similarly, you have the first term, which is gamma m cross b. This tells about the precession of the spins around the magnetic field B. The second and the third term, they are basically the rate of relaxation of the magnetization. So, where the T1, it is the spin lattice relaxation time. We will see about these T1 and T2 in greater detail in the following slides. So, T1 is known as the spin lattice relaxation time, which determines the rate at which the mz returns to its equilibrium value. So, the rate at which the magnetization comes to its equilibrium value, it is the T1. So, you can see that this is mz minus m equilibrium. The T2 corresponds to the, or it is called as the spin relaxation time, which describes the relaxation to the state of quasi-thermal equilibrium. It is observed that T2 is less than or equal to T1. So, spin relaxation time is less than or equal to T1, which is the spin lattice relaxation time. The fourth term, actually it is the fourth term which you see directly contains this value d. It describes the time evolution of the magnetization m when the sample is put into a magnetic field gradient, where m equilibrium is the magnetic field and d is the diffusion coefficient. So, how does the magnetization evolves with time? Now, we talk about what is known as field gradient NMR, which is basically a direct diffusion measurement technique. So, what FG NMR utilizes is the fact that nuclear spins that diffuse in a magnetic field gradient, they experience an irreversible phase shift, which leads to a decrease in transversal magnetization. What it is trying to say is that just before this slide, we saw that there is a magnetization which occurs when your nuclear spin are present in the magnetic field gradient. Now, if there is a diffusion also happening, then the then the magnetization is actually decreased. It leads to the decrease in the transversal magnetization. This decay is observed in a spin-echo experiment. So, what we are trying to say is that if you see again, let me just repeat that the nuclear spins experience magnetization when they are placed in a magnetic field. Now, this magnetization, the value of the transversal magnetization is decreased when there is a diffusion of atoms involved. So, this decay or this decrease is quantified in what is known as the spin-echo experiments. The amplitude of the spin-echo is given by mg t echo is equal to m0 t echo into exponential minus gamma square d, and that's this integral, where this m naught t echo is equal to m naught 0 exponential minus t echo by t2. Now, t echo is the it is the time of the spin echo. So, the duration of the spin echo experiment is written as t echo. M0 t echo is basically the echo amplitudes without the field gradient gt. So, gt is the field gradient. M naught 0 is the equilibrium magnetization of the spin system. So, m naught t echo is the echo amplitudes without the field gradient, and m naught 0 is the equilibrium magnetization of the spin system. Now, for a pulse sequence such as 90, then sometime 180 tau, t echo is equal to 2 tau. That means, if you apply a pulse sequence where you apply for 2 times a tau, then the total time of the echo experiment is equal to 2 tau. Now, if you are in a constant magnetic field gradient G naught, the solution of this equation 1 here is written as mg for 2 tau. Remember, we are talking about this particular sequence. So, mg of which is dependent on 2 tau is equal to m naught 0 exponential minus 2 tau by t2 multiplied by exponential minus 2 by 3 gamma square d g naught square tau q. So, now by varying tau, so by varying tau or by varying g naught is the constant magnetic field gradient, the diffusion coefficient can be determined from the measured spin echo amplitude. So, you as I have said before also, in these wherever these complicated equations come, the intention is not that you memorize this equation, but you try to understand the key features of them. So, for example, in this equation also, if you see that the amplitude of the spin echo experiment, it is dependent on the relaxation time tau, it is dependent on the G naught, and your diffusion coefficient is coming into picture. Now, if I can vary, let us say tau for several experiments, and I can measure the value of the spin echo amplitude, this variation will help me determine the diffusion coefficient. Or other option is I can try to vary the G naught and again obtain mg for several G naught, and that will also help me get the value of the diffusion coefficient. So, this diffusion of spins is followed by FG-NMR, and hence it is comparable to the tracer diffusion, and these FG-NMR experiments permit the diffusion measurements in isotopically pure systems. That is where it is actually in contrast to the tracer diffusion. For tracer diffusion, you require certain radioactive isotopes. So, the equation 2 implies that FG-NMR technique is applicable when T2 is large enough. So, you can have a look at this equation. The T2 when it is large enough, then only you can have sufficient amplitude so that the diffusion coefficients or this signals can be nicely measured, which will ultimately help you to arrive at the diffusion coefficient values. So, a significant diffusion related decay of the spin echo amplitude must occur within T2. Okay, so within this time T2, there should be a significant diffusion related decay which should occur. That means that the D value should be large enough for the fixed T2 and G naught. So, if you have let us say if you choose my T2 is equal to a certain value, G naught is certain value, then the D should be large enough for the decay to occur within that time. Because if there is not much decay, if there is suppose you are varying some parameter and there is not enough change in the value of the amplitude, then you will not be able to have a statistically reliable estimate. If you want to still measure the smaller D values, you require a high field gradients which are provided by pulsed magnetic field gradients. So, examples of PFG NMR, PFG stands for pulse field gradient, include diffusion of hydrogen in metals and intermetallic compounds which are of the order of 10 power minus 10 to 10 power minus 13 meter square per second, diffusion in porous materials and polymeric matrix, and self diffusion of liquid lithium and sodium. So, this is the example which is shown here for the measurement of diffusion coefficient in lithium to in the heat treated and pristine compound of lithium, which is given here. So, this is the variation of D with 1 by T. So, basically the activation energy is also measured here. Then, so this is about the direct measurements. The indirect measurements for diffusion studies measure either the relaxation times T1 and T2 or the line width of the absorption line. Okay, remember when we talked about the direct measurement, there we are directly determining the D by measuring the amplitude of the spin echo experiments. Now, when we want to consider the indirect measurements, let us first try to consider the measurement of the spin lattice relaxation time T1. So, if a magnetic field is applied in the z direction, then you have dmz by dt is equal to mz equilibrium minus mz by T1. So, typically this determination involves two steps. One, that the nuclear magnetization is inverted by the application of an inversion pulse, and then mzt is observed by a detection pulse as it relaxes back to equilibrium magnetization. When you are at the resonance condition where the omega naught is equal to gamma times B naught in an alternating field B1, then the magnetization will precess in the yz plane and the frequency of it will be gamma times B1. Now, here the theta is equal to gamma times B1 into Tp, where Tp is the duration for which the field is applied. So, you basically then convert this theta p is equal to, let us say, pi to theta p equal to pi by 2. From yz plane, it will change to magnetization will change to xy plane. And during precession in xy plane, the voltage is induced in the coil, which is known as the free induction decay, or abbreviated as FID. So, this is the pulse here, and for a time tau you apply, and then this is now a pi by 2 pulse, and this is the magnetization which is written as m tau. So, NMR is basically sensitive to interactions of nuclear movements with the fields produced by their local environment. Now, two mechanisms of interaction in relation to the atomic movements are fairly common. One is the dipole-dipole coupling among the nuclear magnetic moments, and second is interaction due to the nuclear electric quadrupole movements with internal electric field gradients. This happens for nuclear spins I greater than 1 by 2. For both these cases, the thermally activated jumps of atoms, which basically is what is the diffusion process, they contribute to the width of the resonance lines and the relaxation times. Now, let us take the interesting case of the spin-spin relaxation and what is known as the motional narrowing. So, if you only consider for a moment the magnetic dipole interactions for the precision of each nuclear spin, then the B is equal to B naught, the total magnetic field is equal to B naught plus B local, where B naught was the, remember the B naught was the static magnetic field initially that is applied, and B local is the local field created by the magnetic moments of the neighboring nuclei. Now, these dipolar fields which are experienced is proportional to 1 over r cube, and since the nuclear moments are randomly oriented, then the local field varies from one nucleus to another. The dispersion of the Larmor frequency, and to this leads to the dispersion of the Larmor frequency, and therefore to the broadening of the resonance line. So, you have the delta omega is equal to 1 by T2, which is proportional to gamma into delta B local. So, you have the resonance line is broadened because now you see that you have this delta B local, which is the average of the local fields in the sample. So, this is how this B local and this time, so the temporal fluctuations of the local field, which gives rise to what is known as motional narrowing. We will just understand what is that in next few minutes. So, the typical values without the motion of nuclei. So, remember here still we have not considered the motion of nucleus so far. Okay. So, this just that you have several nuclear magnetic moments which are randomly oriented. So, you have broadening of the resonance lines delta omega equal to 1 by T2, which is proportional to gamma times delta B local. Now, typical values without the motion of nuclei, this is 2 into 10 power minus 4 Tesla, T2 is around 100 microsecond, and delta omega is 10 power 4 radian per second. Now, this is referred to as spin-spin relaxation time in the rigid lattice. So, rigid lattice means where atoms are stationary and they are not moving. When the diffusion of atom occurs, the jumps of the individual atoms from one side to another is involved. That means the mean residence time of an atom. So, if it is a rigid lattice, then atom is staying there itself on a particular lattice side. But when you have the individual atoms jumping from one side to another, then you talk about what is known as the mean residence time on a particular site, how long an atom stays on a particular site. And this time is often expressed as tau bar is equal to tau naught into exponential delta h by kBt, where delta H is the activation enthalpy. Now, with each atomic jump into a new site, its nuclear moment will find itself in another local field. Okay. So, for example, if a nuclear moment is present in one site, it is experiencing due to its neighbors a certain magnetic field. Now, the same atom, if it has if it changes to another site, the neighborhood of that atom will change, and therefore it will find itself in another local field. So, this local field sensed by the nucleus will fluctuate between the minus B local to the plus B local. So, if this tau bar, which is the the residence time of the atom on a particular lattice site, if it is very less than T2, which is the time for relaxation time for the rigid lattice, then the nuclear moment will behave as if it is in a new effective local field, which is given by the average of all the local fields sampled. So, for randomly oriented field, this average is very small, and the dephasing between the spins grows more slowly with the time in a fixed local field than in a fixed local field, and these effective local fields of all nuclear moments will be very small, and the nuclear moments will precess at the nearly same frequency. So, this nuclear moments will therefore not lose their coherency as rapidly as during an FID. So, longer the FID is equivalent to higher T2, which is equal to a narrower resonance line. So, for the higher diffusion rates, you have delta omega prime is equal to 1 by T2 bar, 1 by T2 prime, which is equal to delta omega square into tau bar. So, this phenomena is what is known as the motional narrowing. So, this is a schematic of how diffusion contributes to the spin lattice relaxation rates 1 by T1 and 1 by T1 rho, and the spin relaxation rate 1 by T2. So, T1 rho is the spin lattice relaxation time in the rotating frame. So, here this delta omega is equal to 1 by T2 is for the rigid lattice, and as you have as the time as the diffusion happens, then this time is reduced. So, your width starts coming down. So, here you can have either 1 by T1 or 1 by T2, and this due to the diffusion you will see that this becomes more and more narrower. So, the spin lattice relaxation, it can take by either the absorption or emission of phonons, or by coupling of spins to the conduction electrons in metals. The total spin lattice relaxation rate is given by 1 by T1 is equal to 1 by T1 E plus 1 by T1 here dP, and here it is subscript Q. So, the first is due to the coupling of nuclear spins with the conduction electrons, that is why the subscript E is coming here. This is often represented as constant into T, where T is the absolute temperature. This is known as Coringa relation. This dP represents the dipole interaction. So, the relaxation spin lattice relaxation due to dipolar interactions, and this Q represents the quadrupolar interactions, which is actually 0 when I is equal to half, but this is the relaxation time that is coming due to the quadrupolar interactions. So, this is one example of the relaxation rates, spin lattice relaxation rates, which is 1 by T1, T1 rho, which means it is in a rotating frame. Rho represents, so T1 rho basically represents the relaxation time in a rotating frame. So, these are the spin lattice relaxation rates in the laboratory and the rotating frame of reference for a particular compound. So, you can see here the differences that are taking place. So, this is for 1 by T1 and this is for 1 by T1 rho. So these fluctuating fields are described by a correlation function Gt, which is equal to G naught into exponential minus mod t by tau c, where tau c is known as the correlation time, and it is very closely related to the mean residence time between successive jumps, which was tau bar, what we wrote before. And this Fourier transform of this function g of t, it is called a spectral density function j omega, which is a Lorentzian function, and it is written as g0 into 2 tau c by 1 plus omega square tau c square. And 1 over T1 is for the dipolar is related to this j of omega naught by this particular expression. It is dependent on the spin I plus 1 gamma to the power 4 h bar square in a factor of 3 by 2. So the tau c also follows similar behavior as we saw for tau bar, which is equal to tau c naught into exponential delta h by kb. The delta H is equal to activation enthalpy of the diffusion process. So with this, we end today's discussion on the NMR methods, and we will talk about 2 more related techniques in the next video. Thank you.